Miguel. And so the ambition for our project is to sort of design a ecological system and construction process for earthquake-prone residential settlements and landscapes. So really our goal is to fabricate a composite material system that can sort of aggregate and deploy as habitable infrastructure and is produced by readily available materials in Kathmandu, Nepal. So really we want to focus on the relationships between material resonance, earthquake-resistant structures, and fabrication processes. So you may know, in 2015, Kathmandu was hit by an earthquake, and it displaced many, many people. And 3 years later, we all had a chance to go, and they're still rebuilding. And that's probably due to lack of funding and lack of proper materials that they have available to them. So what you see in blue is where most of the buildings were affected. About 1,200 buildings were affected, and most of them were made of Adobe construction. And unfortunately, Adobe construction actually contributes to over 80% of the overall pollution, and it performs poorly in earthquake-prone areas. And that is because?
So as the majority of the buildings were made out of Adobe in the area, so we look at how Adobe fails, and it's mainly because of its high mass and extreme brittleness that it fails in an earthquake situation. So we propose to replace the Adobe with a biomaterial composite, which in the case of our study is mycelium, and which is the sort of like the vegetative interwoven filamentous part of the mushroom, which forms before the mushroom sprouts, and this can be combined with a variety of natural substrates to produce different properties, resulting in a natural polymeric composite fibrous material. And so we looked at some of the existing research which has been done on mycelium, and we see that its mechanical and structural properties are similar to that of Adobe, but with really low density and weight, which is beneficial for our cause. And so mycelium is a biodegradable material, easy to produce. So the biodegradability of the material was important in this case because the Adobe construction, the debris that were formed from it after the earthquake resulted in a high, further pollution of the environment. And so the mycelium material would be easy to produce from local resources, and it's a low cost and minimal pollution material with a high strength to weight ratio. And so we look at precedents of biomaterials in architecture, and which have been flexible formwork, block masonry construction, and 3D printed molds for the material to grow in. Out of these, we are looking at flexible formwork and making a sort of mold from the flexible formwork for the mycelium to grow in, because block construction is not favorable for earthquake situations. So here our research question becomes that can a composite mycelium material be developed to achieve earthquake resilient behavior through manipulation of material properties and geometric configurations while reducing pollution due to vernacular Adobe construction methods in Kathmandu, Nepal?
So moving on to the experimentation, we have computational experiments and physical experiments running simultaneously. We chose to start with our physical experiments to really understand how this material works, and really focusing on sort of the natural growing process, from choosing our substrate to sort of finishing, and how this thing grows and how we can control the moisture and light. So we kind of constructed an environment here at MTech where we were focusing on how we can waterproof and sort of protect from sun, because we need mycelium to grow in cool and drier environments. So we set up 4 experiments using 4 different types of substrates in this sort of block formwork. We found that oat and jute actually didn't work so well because we were probably lacking a clean environment at the time, and we noticed that oat paste is kind of too moist for growing mycelium. So we focused our further research in looking at the composites with aspen and hemp. This is what the substrate kind of looks like in the beginning, day 1, and this is what we can sort of achieve by day 20. So what we noticed is that the harder the substrate, the more dense the resulting composite is. So you guys kind of felt it. This one here is aspen, and this one is hemp.
In the aspen sample, you can actually tell that it has a slightly wooden properties to it. And and
And-
NF is slightly more spongy.
Yes, exactly. And we also noticed that in our formwork, we have to sort of make it of a non-organic or non-fiber system, because when we're peeling off the block formwork, it actually sticks to the mycelium. So anything like plastic, acrylic, that was working better. And obviously we need to improve sort of our sterilization of the environment in order to get this going. So moving into our computational experiments, we wanted to focus on the relationships between sort of the traditional vernacular house, how we can sort of optimize for earthquake resistance, and sort of understand how we can create this formwork geometry in order to propose a new 3 to 4 story building.
So now we're going to the study of earthquakes and how they affect structures. This is just a small refreshment of terms of terminology that we'll be using from now on. So essentially, when approaching earthquakes, there are 3 main techniques. Either you make a structure extremely stiff, which costs money. Either you do a dynamic approach, in which we have things like tuned mass damping, like in the Type A101 building, in which you essentially mitigate the effects of the earthquake through an active system, also expensive and usually for higher structures. And the final one is by increasing flexibility and adapting to the waves of the earthquake and allowing the structure to deflect under the conditions. So we started branching from trees in nature. As you can remember, trees during an earthquake tend not to fall, not to be affected. So we studied the effect, we did a quick run through branching and how the modal frequencies of each individual tend to be lowered when branching is increased. Individual 5 is the one here where branching is. We'd also define a range, and when an earthquake occurs, waves, the destructive waves of the earthquake are within the range of 1 to 6 hertz. And so we want to bring our structure to be there in order for it to oscillate and dissipate energy through branching, which is essentially what trees do, and that's the essence of our project. And so this is a case study in which we start to manipulate either the thickness of the branches or the length of the branches, and for individuals A to B, B being the last one, we can start to see how we can lower the frequencies of our structures. So from this we learn that energy dissipation occurs through the oscillation of elements. So we want various elements to be active in the structure and move during the seismic event in order to dissipate energy efficiently.
So we start by a form-finding experiment where we take the Newar section and the sort of spatial relationships where they're more private on the ground floor and more public on the top floor, and we kind of assign values. We assign values to those relationships, where the more private the space, higher sort of the repeller, so that we can sort of let these agents avoid those spaces. And then also taking from our branching principles, trying to add branches or adding a system in addition to this sort of sectional relationship, so that we can get our agents to sort of have moments of separation and moments of these branches. So we run the agents, and we took the behavior sort of inspired by the mycelium growth at the molecular level, but we kind of focus on sort of manipulating the growth rate and sort of the attraction forces, like I mentioned, for the earthquake branching principles. Then we look at the critical nodes, we see where these agent trails sort of are more dense, and we start triangulating between them to sort of create our structure. And so this was, like I said, a form-finding experiment, and we were able to get a variety of 3 to 4 story building proposals. So what we can do, going back to our earthquake branching principles, is what we can change the length, we can change the diameter of these beams, and we can change the nodal mass of where these critical connection points are.
So in like our next step will be to set up a GA with all these parameters that we're using. We are not there yet, but we're doing this. And we'll have a fitness criteria in which we will want to have our model frequencies occur in the range we want, minimize self-weight displacement, and minimize material usage. So structurally, that's what we're looking at right now. These are our examples of what we did. if we start with a branching system like the one above, we know that this is not a feasible geometry for a building. But if we can achieve something like the last example, in which we have, imagine, towers oscillating within the system separately, then we can achieve this branching behavior. This is proven through experimentation.
So we did the structural analysis on these forms, and we noticed that an open branching system is more desirable over a closed one due to sort of overall lower displacement and modal frequencies. The displacement values here are actually scaled up by 5%, just so that you guys have a visualization of how this thing moves. So they're not absolute values, but we understand that at least by this experimentation, we know that the modal frequencies were out of range. So
this was our first run with 4 geometries we chose from our agent iterations. As we can see, they are starting to come to range, but they're still beyond the 1 to 6 hertz earthquake range. So we do one more iteration, we subdivided the mesh even further, and we started to achieve some branching elements. At this point, the architectural consideration is not clear. We envision that maybe they can be separate towers or just sole elements meant to dissipate energy.
But the good thing in this example is that you can clearly see that the individual towers that are sticking out are dissipating all the energy, which leads to the rest of the structure not oscillating during an earthquake branch. So that iteration proved to be way more close to the range we want to achieve. So that's through our experimentation, we've managed to achieve a closer result to what we want.
So sort of how do we fabricate this now, right? We have this crazy form. So we wanted to go back into the physical experiments and focus on our flexible formwork.
So for the physical prototyping, we took a part of this geometry which we can sort of, which can be modified and replicated all over the system. And so the aim was to develop a sort of construction technique derived from modular parts, by modulating these parameters such as the beam length, the radius of the discs, and the distance between the node and the beam, to be for it to be able to create the entire mesh system that you see here, and for it to be a sort of non-specialized, easy to create system by a non-specialized labor. And so in the beginning of this, we're just starting to create this prototype, that one, and we realized that there are some problems which we have now, that once we are bringing the ropes in tension and we start to wrap the flexible fabric around it, it drastically reduces the radius of the beam that we have designed it to be. And so we need to maybe add more discs or create more tension, and the most critical drawback of this is right now that the precision of the system, because this geometry needs to be highly precisely fabricated for it to do what it's meant to do. So for that, we are kind of looking at some sort of a guiding tool which can be created.
So what have go.
As a final note, we want this to be labor intensive.
Oh yes.
This system to require a lot of man hours to be constructed in order to generate employment within the calendar region, which is one of our...
Yeah, because it goes back. I mean, we have over...
That's why we're keeping it low tech.
Because we have people sitting there. We need to make it work. So what have we accomplished? We sort of established our logic for our form-finding experiments, which need to be refined, obviously. And also, we've established sort of how that loops into our structural system to increase earthquake resistance. And we sort of have sort of the limitations of this sort of fabrication process. So it kind of leads us to the question for the unmarked phase. Can we sort of facilitate the fabrication process by developing an interactive application that increases precision and help visualize complex geometries? So thank you.
I have a question on the mycelium. By the end of the presentation, I was a bit lost about where in the mix was the mycelium. Is it supposed to be applied afterwards, or?
It's inside.
So we make the mycelium former, then we use it as a mold to fill the mycelium in.
Okay.
And
So it's actually part of the mix.
This is how we're just preparing the mix. And
Now that makes sense. And I think, it's really interesting. At the moment, it feels like you guys are focusing on the, let's say, the straight elements of this lattice. But on the diagrams you were showing, the more complex areas of the systems are in the nodes, or appear to be in the nodes. So if you want to focus on the fabrication method for this, I think the nodes will be kind of a really important area to focus on.
Yes, of course.
The development. And again, I think it's also a matter of thinking how are you guys going to, or thinking to apply this. When you talk about the tower, I was thinking, are you imagining an actual tower, or just a tower?
we might have failed to mention this. Generally, the wiring architecture is based in a 4-story house. Like their spatial distribution is vertical, and so their family nucleus is organized in a vertical fashion. So generally, it's a 4-story building.
So if that's the case, then you certainly need to address the spatial qualities.
Yeah,
yes.
So
at the moment, we're let's say filling the whole volume. So what happens when you get one of these members, crossing a very important area you have open or something? Basically, you also make sure that this will allow for the space to function, for the building to function as well.
Yeah.
Also to verticals of slabs and also all other stuff that you
Yes.
usually put in buildings.
All the architectural considerations.
But really interesting.
I think building on your point of the nodes, I think actually, it would be worth considering, as you say, prototyping that, but then almost you might find where are you going to make the connection. And it may not be, especially in terms of, as you know, as you've highlighted, the stiffness of the system is going to drive the natural frequency of it. And so the stiffness of the nodes is going to be, again, that continuity is going to be paramount. So you might actually be able to do a quite clever study on where is the point to do the break. It might not be at the node. It might be at the midpoint along the line. It might be probably 3/4 along or somewhere. So I think that's a study that's really worth looking at. Also, obviously the stiffness, capturing the stiffness correctly, but also as you highlighted as well, the mass and the distribution of the mass in the system. So I think, I'd certainly like to see that you've incorporated the allowance, if nothing else, for the extra mass that's going to be in the system once you've incorporated in the really annoying things like horizontal slabs.
Yes.
A whole load more mass in the system. So I think you need to make sure you've got that allowance. But equally then, making sure you're accommodating, okay, you've got the primary system is what's got the continuity. So I think something else which was quite interesting, that you had a sort of taller tower that's working as an oscillating thing to dampen the system. So you might have slightly different construction tolerances or movement tolerances in different parts of the system of building. I think highlighting that and demonstrating you, because that actually could drive the different types of construction and the different types of uses of the space. You're probably not going to want to do some plumbing right up to the top of that tower. Really flexible pipes or maybe other parts. I mean, that could be almost providing some sort of dialogue between the structural solution and the spatial usage as well. Not to mention the construction tolerances. Really weird stuff.
It's very strange. I've got one question on that.
Yeah.
Because which relates to some extent to some. I mean, what I would be interested to know, apart from obviously, logically you want to try to grow your structure as a continuum, if you like, without discontinuities, but on the other end, discontinuities may be helpful for other reasons. My question is a very simple one, which just crossed my mind now. If you take the two samples, the softer one is the one with hemp,
Yeah, the
the
hemp.
stiffer one is the one with
Aspen.
My question is, okay, are these two, if you take two aspen,
Yeah.
a bit more rigid, are they joinable by any
Like,
technique?
like
In other
a,
words, can you make a joint, a mechanical joint
Mechanical.
between two bits made of that stuff?
Can you grow one?
I mean, we can,
Generally, it will be a continuously grown structure.
yeah,
Yeah, no, I know,
Yeah,
but at the same time, okay?
like a gradient between aspen and, like a gradient between, like an
What I'm
aspen.
saying is if I got two bits
Right,
coming out, okay,
Yep.
can I join them together mechanically? And is that joint going to have any performance?
Right.
I'm just curious because you mentioned the Japanese pagodas,
yeah, yeah,
and there everything is coming out of the joints,
Mhm.
and the joints are made in wood,
right,
okay, and yet they are still there.
Mhm.
So after many earthquakes. So what I'm saying is that there is, don't forget the fact that the joint may be beneficial, okay, in more than one way, partly to solve problems, geometrical problem, complexity, whatever not, partly because they may contribute actually to some of the performance level anyway.
okay,
But out of interest,
yeah,
you know, it would be really quite interesting to know if these things can be joined. And what is the load-bearing capacity of the joint to make this stuff.
How do you imagine when you say it's continuous? How do you imagine that?
Like so,
Growing something.
yeah.
Is it something, I mean, you can look at the way concrete is cast, for example, in fabrics, and there are successive lifts. And the next lift is poured when there's still possibility of a molecular bond between the previous pour and the new pour. So maybe this has to grow in a closed seal. Okay. But there's a point where you could release one at the top of the container. Or
add more, yeah,
Yeah.
Or there's sufficient stiffness. I don't know, I think that's.
It's something super interesting that you haven't checked.
Yeah.
I remember I once tried to do a sculpture, and it actually started to work. And it surprised me is the relationship or the interaction between the textile, flexible textiles and aggregates. And because you have this thing, I don't know what it is.
it's just wrapped, yeah,
It's,
yeah,
no, there's a thing inside. If you put, say, a media, like a tie, and you put this thing inside, it does arch to the edges, to the point that it doesn't let the load down. So you can make like a build on it, like a natural, I mean, if you put, imagine a tie like that, and it's like flexible, and you can put a bulb like that, and you keep putting stuff on top, it will not pull down because it arches to the sides and it brings it in. So I think there's quite a lot that you can study of how this is not aggregate, it's something, it has more cohesion than aggregate, more than sand. They actually start to breach out and create those things naturally by the way in which you put them down. And then create these things just by the relation between the flexible fabric and this thing, which is not aggregate, it's a funny thing, it's like grass. So if you put grass, just by the way it works, it will add sides, it will, the thing outside will try to pull it in, and it literally blocks the top. It's like a, it's like a pipe that gets clogged. So you can use the clog as a way of parsing the whatever the fact. It's super, and you are playful enough to play with that. Because another group would be like, oh, this, but you guys are into the mess and everything. So I think that sort of like clogging effect can be a nice way of fabricating these things, the node, whatever. And I think it will give you constraints to then go back to the model because the model looks a bit out of the blue. And it should be. I think it's nice you've done it, but why not feed it back with a couple of stuff?
okay.
Which I think, yeah.
Cool. Thank you.
Thank you very much. Please join me.